Yeah, today we are going to discuss about the spectrophotometer instrumentation, UV visible spectrophotometer instrumentation. So I have just made the diagram, the general layout of the UV visible spectrophotometer instrumentation. So here we have the light source, basically having deuterium and hydrogen lamp for the UV region and tungsten lamp for the visible region. And this is the L1. L1 is basically a lamp which is a light source for UV light as well as for the visible region, and followed by a slit. Slit is nothing but S1. The purpose of any slit is to control the intensity of light radiation. After slit we will be having the monochromator MC. The monochromator is having lot of mirror components, M1, M2, M3, lot of mirror components are there in the monochromator. And these monochromators are basically, there are two types. One is called prisms, another one is called gratings. The monochromators acts as the filters because they disperses the wavelength of uniform intensity of radiation. So that means the purpose of any monochromator is to convert the polychromatic light into monochromatic light. Next comes your S2. S2 is another slit which controls the intensity of light radiation. Then comes your SH. What is called SH? SH is the sample holder which holds your sample cell. Right? So this inside this only you will be having your sample which is dissolved in a suitable solvent, because for UV visible spectrophotometry, if the compound is just obeying the Beer-Lambert's law, the sample has to be properly dissolved in suitable solvent, right? So therefore, sample dissolved in a suitable solvent will obey the Beer-Lambert's law, where A is equal to ABC. So what will happen? This is the intensity of incident light radiation which is hitting your sample cell, and some of the light radiations are absorbed by the sample, which I have given as IA, and some of the light radiations are getting transmitted. Suppose if 100% radiation is coming here, if 20% gets absorbed, so 80% of the light radiation will be getting transmitted. So this is the meaning of that. And the transmitted light radiation will be falling on the detector. The transmitted light radiation will be just falling on the detector. So what is the purpose of detector? The detector detects the transmitted light radiation, where it converts the light energy into electrical energy. And from the detector we have an R. R is nothing but recorder, right? So the recorder records the electrical signal from the detector. That is the purpose of any recorder. And DC is basically a printer, right? When I talk about the sample cell, we are using different type of sample cells. One of the very important thing you should remember that the quartz quartz are the fused silica for the UV region. When you want to do for UV region from 200 to 400 nanometer, we are using either quartz or fused silica quartz. When you want to do it for the visible region, colorimetry region, we are using the simple glass quartz, right? Because glass, if you are using glass quartz for the UV region, glass absorbs the UV visible radiation, because glass is made up of sodium borosilicate. They absorb the UV radiation. Therefore, we are not preferring to use the glass quartz for UV visible radiation, right? So this is the reason, and this is the general instrumental layout for any spectrophotometer, whether it may be a single beam or double beam. We are using the similar general pattern of instrumentation as such, right? Now we will discuss some of the important components. As I already told, we are going to discuss in detail about these prisms and gratings. The monochromator is generally basically made up of two components. One is called a prism, another one is called gratings, right? They act as the dispersing elements, because dispersing elements means they filter it out. Suppose for example, if you are using 400 nanometer to 800 nanometer. If you are using 400 to 800 nanometer, so I want to do my analysis for visible region at an accuracy for my sample at 425 nanometer. Okay. Suppose for example, I am passing the light radiation for, if I keep the filter at visible region, it will give the light radiation from 400 to 800 nanometer. But my sample wavelength is only 425 nanometer. So the rest of the radiations are unwanted radiations. So I have to filter it out. For that purpose, I am using the monochromators, which may be either prism or gratings, right? So if I use this prism or gratings, how accurately this 425 nanometer will be delivered to the sample cell? This is very, very important thing, right? So when I discuss this aspect, the prisms and the gratings are acting as the dispersing elements. They disperse the radiation of specific wavelength, say 425 nanometer. Or in other words, the prisms and gratings convert the polychromatic light radiation into monochromatic light radiation, right? What is the function of the prism? The prism is worked based upon the size and the refractive index. These are the two important crucial things for the proper working of prism. and the band pass is plus or minus 5 nanometer. What is called the band pass? Band pass means suppose my sample wavelength is 425 nanometer. If I use the prism, I will be getting 425 plus or minus 5 nanometer. Okay, that means it may be either 420 to 430 nanometer. Okay, so 420 to 430 nanometer. That means plus 5 nanometer and minus 5 nanometer, right? So therefore the band pass filter will be around plus or minus 5 nanometer. So if you want to have very lesser band pass for your monochromator, you will get more and more accuracy for your experiment, right? So prism, normally the band pass will be plus or minus 5 nanometer. Whereas for gratings, what are called gratings? Gratings are nothing but the rulings made on elements like glass or alumina or quartz or alkyl halides. These are the rulings. Basically, they are the rulings made on the elements like glass, alumina, quartz or alkyl halides. And the number of rulings in the glass will be 20 to 3600 grooves or lines per millimeter. You just imagine. The grooves means very small, minute projections in the glass. That will be around 20 to 3600 grooves or lines per millimeter. And these lines or the grooves of the rulings act as the dispersible elements. These small rulings, right? These small rulings, the grooves of the rulings, they act as the dispersible element. Particularly, they disperse the wavelength, radiation of uniform wavelength, right? So some of the gratings are made up of holographic laser gratings where they are having double coatings. That is, they have a epoxy resin as a secondary coating mold followed by a single alumina coating, right? So they are more accurate and they have the band pass of plus or minus 0.1 nanometer. Just imagine. These holographic gratings have the band pass of plus or minus 0.1 nanometer. That means they will send the radiation of 425.1 nanometer and 424.9 nanometer. That much accuracy you will be getting the wavelength, right? So this is more accurate. Holographic gratings or the laser gratings are made up of epoxy resin as a secondary mold coating followed by a single alumina coating, right? So this is all about the various components of this thing. Now, when we talk about the sample cell, this sample cell is also important. The sample cell I told basically for dilute solutions we use the path length of 2 to 3 centimeter. Normally the sample cell width, the width of the sample cell will be 1 centimeter. Right? The sample cell path length will be normally 1 centimeter, but in case of more dilute solution we use the path length, higher path length of 2 to 3 centimeters. If more absorbance is needed, sometimes if you want to run the experiment with more absorbance, 90% absorbance is necessary, only 10% should be transmitted. In such cases we are using the half silvered quartz, because inside the half silvered quartz the light radiation will stay for a long period of time. So in that case, for more absorbance we are using half silvered quartz as such. And for aqueous solutions, when you want to do the experiment on aqueous solutions, particularly in biochemistry practicals, more aqueous solutions we are using like dissolving in blood sample, all these things, we are using the polystyrene cells. They will give more better readings as such, right? So this is all about the types of sample cells what we are using for UV visible spectrophotometry. And coming to the detector, these detectors are also called as photometric detectors. Basically they are called as photometric detectors. These detectors are also called as photometric detectors. Photometric detectors means they are converting the light energy to electrical energy, or simply they will convert the photons into electrons. So what are all the types of detectors used in UV visible spectrophotometry? One is barrier layer cell, which is also called photovoltaic cell, which is a very cheap instrument. And the next important thing is that phototubes, which are also called photoemissive cells, which we will discuss all these detectors in the next class. So phototubes are photoemissive cells. And the third one is photomultiplier tubes, which is more important and widely used. And then we are also using semiconductor based detectors such as silicon photodiode. Okay, so this is also having when the energy gap is very less, we are using this silicon photodiode semiconductor based detectors. They also give some good accuracy, right? So these are all the 4 types of detectors we are using in UV visible spectrophotometry. Now coming to this double beam spectrophotometer. Single beam spectrophotometer means only one beam. This is an instrumental component of single beam spectrophotometer. Whereas in case of double beam spectrophotometer, there is a double beam. Beam in the sense the light radiations will be divided into 2 equal halves. That is called double beam spectrophotometer. So here we will be having the lamp or the light source, deuterium or hydrogen. So which one you want to use it, you can select the mirror as such, and it is connected with the monochromator. The monochromator disperses the wavelength of uniform intensity of radiation, and from the monochromator it is just going to the optical chopper. What is this optical chopper? This optical chopper is basically the half silverized mirror or beam chopper which splits the radiation into two equal half. What is the meaning of that? If 100% radiation is coming here, okay, so 50% is going here and another 50% is going here, right? So if you keep the optical chopper, the 100% radiation will be splitted into two equal half. 50% will be going to the sample cell 1 and 50% will be going to the another sample cell 2. So here you can use initially with both the sample cell with the blank, and then after adjusting the absorbance, then after that what you can do, you replace one sample cell with one sample cell with the sample solution and another one with the blank, and then take the reading as such, right? So the purpose of optical chopper is to chop the radiation into two equal half. So therefore what will happen, it is going to sample cell 1 and sample cell 2, and after that we are keeping some mirror, and then it is connected with the beam combiner. The radiation, the transmitted radiation will be combined with the help of beam combiner from both the sample cells, and that is passed to the detector. So detector is basically the photomultiplier tube, and detector is attached with the recorder. So this is called double beam. Double beam in the sense the beam is splitted into two equal half. The radiation intensity will be splitted into two equal half. So that is the purpose of optical chopper or the beam chopper or half silverized mirror. Why we are doing this thing? So if you do in this manner, it is not necessary to adjust every time for the blank as well as for the sample. The absorbance, see, when we are keeping the blank is an inert solvent which should not absorb any radiation. When you keep the blank, the absorbance should be 0. Okay, after that you remove the blank and keep the sample and record the reading. Okay, so why we are doing here like this? The advantage is that it is going for the fast scanning. When you use the double beam spectrophotometer, the scanning is very fast. Why? Because in single beam spectrophotometer instrument, for every sample we have to adjust the blank, then remove it out, then you keep the sample and record the reading. But here it is not necessary. Once you adjust the blank once, after that you remove the blank and then you keep the sample and change the sample and then directly take the reading. Okay, so the time consumption will be reduced in case of double beam spectrophotometer, and scanning is quite possible in a faster time period. So this is a biggest advantage of double beam visible spectrophotometer, UV visible spectrophotometer. Why? Because with the help of this double beam optical chopper or half silverized mirror. So this is all about the instrumentation, particularly the construction and the working of the UV visible spectrophotometer. So I hope you understand in a very clear manner. Thank you, my dear students. Thank you very much.